This is my example of a polarity problem. First, we are going to look at the question being asked. The question we are being asked is how many of these molecules are polar. These are the three basic steps we'll use to solve the problem. The first step is to draw the Lewis structure. The second step is to identify bond dipoles by using differences in electronegativity. And the third is to identify the net molecular dipoles based on the molecular geometries. Let's begin to solve the problem for each molecule one by one. We can do this correctly by using the rules we learned about Lewis structures. SO3 is the first molecule we will look at to decide if it is polar. There is a total of 24 valence electrons. To draw this Lewis structure, we begin placing the valence electrons on the outside atoms first. We have used all 24 electrons, however, the S atom does not have a full octet, so we will have to make a double bond between an S and O atom. Now let's look at the bond dipole. The highest electronegative atom, which is O, will have partial negative charges because the electrons drift towards the atoms with the highest electronegativity. That means there will be a partial positive charge on the S atom. The bond dipoles are going to look like this. A tail that's positive on the S heads towards the O on the outside. There will be two other dipoles going this way and this way. The arrows show you the direction of the charge separation. The length of the arrow represents the magnitude of the charge separation. In order to find out whether the bond dipoles cancel or not, we have to look at the three domains around the center atom. Three domains is a trigonal planar molecular geometry. Since all of our domains are the same, we will have no net dipole. Since there is no net dipole, it makes this molecule nonpolar. Next, we will look at OF2 to see if it is polar. There is a total of 20 valence electrons. Once again, to draw the Lewis structure, we begin placing the valence electrons on the outside atoms first. We have to make sure each atom has an octet. We have used all 20 valence electrons and each atom has an octet. Now let's look at the bond dipole. The highest electronegative atom, which is F, will have partial negative charges because the electrons drift towards the atoms with the highest electronegativity. This means there will be a partial positive charge on the O atom. The bond dipoles are going to look like this. A tail that's positive on the O heads towards the F on the outside. There will be another dipole going this way. The arrows show you the direction of the charge separation. The length of the arrow represents the magnitude of the charge separation. In order to find out whether the bond dipoles cancel or not, we have to look at the four domains around the center atom. Since there are four domains and two of the domains are lone pairs and two of the domains are bonds, OF2 has a bent molecular geometry. We have an F and two O's on the outside, so the dipole goes from the F out to the O's. Because of the molecular geometry, the net dipole will be going down. This is the net dipole. The dipoles in the bond don't cancel because of the molecular geometry being bent. There is a net dipole in this molecule, so it is polar. Now we will look at BeCl2 to see if it is polar. There is a total of 16 valence electrons. First, place the valence electrons on the outside atoms and make sure each atom has an octet. We have used all 16 electrons, but the central atom Be does not have an octet. This is okay because Be is an exception to the octet rule. Now let's look at the bond dipole. The highest electronegative atom, which is Cl, will have partial negative charges because the electrons drift towards the atom with the highest electronegativity. This means there will be a partial positive charge on the Be atom. The bond dipoles are going to look like this. A tail that's positive on the Be heads towards the Cl on the outside. The arrows show you the direction of the charge separation. The length of the arrow represents the magnitude of the charge separation. In order to find out whether the bond dipoles cancel or not, we have to look at the two domains around the center atom. Since there are two domains on the central atom, the molecular geometry is linear. Since all the domains are the same, there is no net dipole, making it nonpolar. Now we will look to see if CCl4 is polar or nonpolar. There is a total of 32 valence electrons. Placing valence electrons on the outside atoms first, we have to make sure each atom has an octet. We have used all 32 electrons and the central atom C also has an octet. Now let's look at the bond dipole. The highest electronegative atom, which is Cl, will have partial negative charges because electrons drift towards the atom with the highest electronegativity. That means there will be a partial positive charge on the C atom. The bond dipoles are going to look like this. A tail that's positive on the C heads towards the Cl on the outside. There will be 3 other dipoles going this way and this way and this way. The arrows show you the direction of the charge separation. The length of the arrow represents the magnitude of the charge separation. In order to find out whether the bond dipoles cancel or not, we have to look at the 4 domains around the center atom. 4 domains is a tetrahedral molecular geometry. Since all of our 4 domains are the same, we will have no net dipole. Since there is no net dipole, that means this molecule would be nonpolar. Lastly, we will look at O3 to see if it is polar or nonpolar. There is a total of 18 valence electrons. When you place the valence electrons on the outside atoms, make sure each atom has an octet. We have used all 18 electrons, but the central atom O does not have an octet, so we will have to make a double bond between one of the outside O's and the central atom. For this specific molecule, we will not look at the bond dipoles, because all of the atoms have the same electronegativity. Since there are 3 domains and one of the domains are lone pairs and 2 of the domains are bonds, O3 has a bent molecular geometry. Because of the molecular geometry, the net dipole will be going down. This is the net dipole. The dipoles in the bond don't cancel because the molecular geometry is bent. There is a net dipole in this molecule, making the molecule polar. Now we will look at the problem again. The original problem asks, how many of these molecules are nonpolar? What did we find? 3 of the molecules were nonpolar because there was no net dipole. 2 of the molecules were polar because the domains were not all the same. That means that out of these 5 molecules, 2 of them were polar. Now we are going to look at some common mistakes people make during these types of problems. The first mistake people often make is drawing the Lewis structures. People sometimes draw the Lewis structures wrong because they may have counted the number of valence electrons incorrectly. Another common mistake people often make is forgetting the exceptions to the octet rule, which could lead to putting the wrong number of valence electrons around the center atom.